In this video, I want to go over the process of solving linear systems, or in other words, determining, given a linear system, what its solution set is. We're going to do this in two steps. The first thing we're going to do is we're going to look at linear systems that, for whatever reason, are easy to solve. These are a very specific type of linear system known as triangular systems, which we'll start with, and then a slightly more general type, which are known as systems in echelon form. Once we know how to solve these types of linear systems, we're going to apply a very fundamental principle of problem solving, which is to try to take any linear system and turn it into a linear system that we know how to solve. So we'll look at transforming linear systems. This will bring up notions that I'll define in the video of what equivalent linear systems are, how we can take one linear system and turn it into different linear systems that are equivalent to it, and whether we can always use this process to accomplish what we want. That is, if we can take a linear system and turn it into an equivalent linear system in echelon form, then we'll be able to solve it. So let's start off with triangular systems. Here is an example of a triangular system. Now you might look at this and say, this doesn't look like a triangle, right? But if I write my terms in a better way, I'll actually get a triangle. I've already done this, but I'm going to pull this up here. When we're writing linear systems, we should always write them in some sort of nice way, right? So instead of aligning the first term of each system, I should align my terms by variable. And I should align my equal signs, and I should align my constants. And when I look at it like this, I can see the triangular shape, right? This kind of looks like a triangle if I draw this shape here. Now, what's the technical definition of a triangular system? I'm not going to write it down because I think you probably already get the sense for what I mean. But the first equation will have a non-zero coefficient on x1. The second equation will have a zero coefficient on x1 and a non-zero coefficient on x2. The third equation will have zero coefficients for x1 and x2, and then a non-zero coefficient on x3, and so forth. So that's what it means for a system to be triangular. And when we have a triangular system, we can use this process known as back substitution to solve it. So what is back substitution? Well, the basic idea is that from the bottom equation, we know what x4 is. And because we know what x4 is, we can figure out what x3 is. And then we know what x4 and x3 are, so we can figure out x2. And finally, we know what x2, x3, and x4 are, so we can figure out what x1 has to be. So let's actually do that. So the bottom equation, 4x4 equals 4. When I divide both sides by 4, I find that x4 is 1. Not so bad. Let's move on to the next equation. x3 minus 5x4 is minus 20. I can plug in that x4 is 1. And when I solve for x3, I get that x3 is minus 15. Let's move up again. Our next equation is 3x2 minus x3 plus 10x4 equals 43. If I plug in these values, I don't know what x2 is yet. x3 is minus 15. x4 is 1. And when I solve for x2, I find that x2 is 6. And then finally, I should go up. I have my final equation, minus x1 plus 2x2 plus x4 equals 16. When I plug in the values that I've found, I find that x1 is negative 3. And then just to finish this up, it's best to write our solutions in some sort of order, right? I want to put them all in one place. So I'll say x1 equals minus 3, x2 equals 6, x3 equals negative 15, and x4 equals 1. This is the only solution to this system. And we should go back. I'm not going to actually do this, but I'm going to point out it's always worth checking your answers when you get a unique solution like this. If I plug these numbers in, right? If I plug in negative 3 for x1 and 6 for x2 and negative 15 for x3 and 1 for x4 into each of these equations, each equation will be true, right? When I plug it into the first equation, I'll get 16 on the left-hand side. When I plug it into the second equation, I'll get 43 on the left-hand side, and so forth. So we can check our answers. All right, so if we have a triangular system, we can use back substitution to come up with a solution. But you'll realize that this can't always work in the sense that there's no way that every system can somehow be solved by using triangular systems, because just doing one example, I hope you can convince yourself that a triangular system will always have exactly one solution. This process will always work. But we already know that linear systems don't always have exactly one solution. They could have no solutions, and they could have infinitely many solutions. So there must be some other nuance here. So we can't always hope that triangular systems will allow us to solve linear systems. So we're going to have to allow for something a little bit more, that is more not quite triangular systems, and that's what's known as a system in echelon form. So let's look at an example of a system in echelon form. So here's an example of a system in echelon form. And notice I wrote it in a nice way already, right? Even though I didn't have an x5 term in the first equation, I still stacked my equations up, lining up the x5s. What makes this system in echelon form? Well, it's not triangular, but we have this similar sort of staircase pattern as we move down and to the right. And the idea is that in a system in echelon form, you have your first variable with a non-zero coefficient in the first equation is x1, or it's whatever it is, it's the first kind of non-zero variable. And then as you move down to equation 2, that term, this x1 term, the first non-zero variable, has a zero coefficient. So as you move down, the index of the variable with the first non-zero coefficient always increases, right? So we go from x1 being the first variable with a non-zero coefficient to x3 being the first variable with a non-zero coefficient to x5 being the first variable with a non-zero coefficient. And I'm already really tired of saying the first variable with a non-zero coefficient. And so let's put some terminology in here. When we have a system in echelon form, we would call x1, x2, not x2, x3, and x5 leading variables. That is, they're variables who are the first variable with a non-zero coefficient in one of the equations. And we call x2 and x4 free variables. Right, one of the values of terminology is to not have to constantly say long, convoluted sentences to describe things, right? So a leading variable is these three things. When we're in echelon form, the first variable in an equation in order, and the free variables are all the other ones, the ones that don't lead off any equations. So how can we solve a system in echelon form? Well, let's just try what we did with triangular system. Let's do back substitution. And maybe I'll put a question mark. I mean, it's going to work, but we're going to have to change something. So it's not really clear that this should work. I'm going to copy this thing just to move it down a little so that we have space so we can see what we're doing. So let's try to do back substitution on this system. Starting with the bottom equation, things look good. We have that 6x5 equals negative 18. And so x5 is negative 3. That's great. Let's move up an equation. minus x3 plus 3x4 plus 7x5 equals minus 15. And when I plug in negative 3 for x5, what is going to happen? Well, I haven't gotten rid of all the variables. And so this is weird, right? It doesn't seem like I'm going to be able to solve this by back substitution. But actually, if you think about this, you can realize that I have 3 equations and 5 variables. And when I have fewer equations than variables, I'm never going to get exactly one solution. I could have no solutions, or I could have infinitely many solutions, but I don't have enough information to narrow things down to a single solution. And so things should look different. And so the fact that variables still live on, that I can't really get rid of everything, actually makes sense in some ways. And so what I'm going to do to kind of show you the process here is first I'll just solve for x3. So I'll get x3 all by itself. I don't know why I wrote that in highlighter, but so if I move everything around to get x3 all by itself, what I get is that x3 is 3x4 minus 6. And I have not successfully gotten rid of x4. Here's the thing. I'm never going to be able to get rid of x4. It's not possible. And so what I'm going to do is I'm going to just call x4 something else. Because x4 can actually be anything. So I'm going to call x4s. This is what's known as a parameter. And once I decide that x4 is s, I have that x3 is 3s minus 6. Said another way, in this system, I can put any value in for x4 and I'll still get a solution. That's what s is representing. It's saying x4 can be anything. You choose a value for x4, you're going to still be able to get a solution with the other variables. All right, let's move along and suspend disbelief if you're kind of unclear on why exactly I did that or why I was allowed to. Let's move to the final equation. I have 3x1 minus 9x2 plus 2x3 minus 3x4 is 21. And now I'm going to plug in what I already have. So x1 and x2 have not been solved for. x3 is 3s minus 6. And x4 is s. And so I end up with this. And again, I have this issue. I have 2 variables left. But if you take a step even further, and this I don't think is obvious, but we have not just fewer equations than variables, we have 2 fewer equations than variables. So it actually turns out that we really lack a lot of information. We need a lot more. And so what we actually need to do is we need to do the same thing we did before. It turns out that no matter what we choose for x2, this thing's always going to have a solution. And so we should just call that thing something. And if I call it x4s, well, I can call, let's actually, yeah, I'll do this. I could do this in a number of ways, but let's call x2 t. Now, if we had a lot of parameters, maybe we would start calling them s1 and s2 and so forth. But x2 can be anything. And if I plug this in, and I solve for x1, I end up getting that x1 is 11 minus s plus 3t. And let's put this all together in the same spot. x1 is 11 minus s plus 3t. x2 is t. x3 was 6s minus 1. x4 is equal to s. And x5 is the only variable that has to be set at a certain value. It's -3. All right, so we've solved this system. This is our solution. And this may seem unsatisfying, right? We've solved our system here, and I guess I can make a note. Getting ahead of myself here. So S and T are any real numbers. I could set S equals to 1 and T equals to 3.7, and that would give me a solution. I can set the two of them equal to any pair of real numbers, and I'll get a solution to this system. And if this is surprising, maybe you can realize that, well, if we're going to have infinitely many solutions, something like this did have to happen, right? There was no way that we were going to get infinitely many solutions, but then also be able to specify exactly what each variable was. So this is our solution set. This is our complete set of solutions to this. It's admittedly, it's a bit tougher to check your work, right? I mean, you could plug back these expressions into the system and confirm that they worked, but that's a little messy. Or I guess you could choose a value of S and T, get specific values for x1, x2 through x5, and plug those back in and confirm that they worked, just as a bit of a sanity check to see if your solution worked in that specific case. All right, so if we have a system in echelon form, we can also solve it by back substitution with this added step where, if we look back, the free variables end up equaling parameters. That is, they're allowed to equal anything, and so we call them something. In this case, I chose S and T. S1 and S2 would be good as well. You'll see some places they'll just say x4 equals x4, right? Leave it as x4, but there's actually good reason not to do that. It can result in confusion later when we do other things. Okay, so we're halfway there. We've done half of what we wanted. We know how to solve triangular systems and systems in echelon form. Now, we want to transform linear systems into systems that we know how to solve. So, in other words, if I have, some linear system that is not in echelon form, not triangular form, how do I solve this thing? So my goal is going to be to transform any given linear system into echelon form. And I should mention, because I didn't say this yet, triangular form is a specific example of echelon form, right? A system that happens to be in triangular form is also in echelon form, right? The leading variables increase in index as we move down the equations. There just happen to be no free variables when you have a system in triangular form. So I'll just refer to systems in echelon form, and sometimes when we get a system in echelon form, it's also in triangular form. That's a more specific possibility. So I want to transform this to echelon form. Maybe it'll be triangular form. Who knows? And the whole idea here is that there's a notion of equivalent linear systems. So I want to transform linear systems. Two systems are equivalent, we'll say, if they have the same solution set. So if the same values of the variables, maybe in this case we're looking at an equation in x, y, and z, two systems are equivalent if the same triples of x, y, and z make both equations true. So anything that makes the first set of equations true also makes the second set of equations true, and vice versa. Any set of triples that makes the second system true also makes the first system true. That's what it means for two systems to be equivalent. And what we're going to do is we're going to try to take systems and transfer them into other equivalent systems that look nicer. So there are three things that we'll do to systems that won't change the solution set, that will change them into equivalent systems. And the first one is very easy to understand. If we switch two equations, that is, we take equation 1 and equation 2 and put one on top of the other, flip their order, we don't change the solution set. I think this is relatively obvious, right? We haven't changed the equations, we've just changed where we wrote them. Also not hard to see, if we take one of the equations and multiply it by a non-zero constant, like we multiply all of the whole equation, the left-hand side, the right-hand side by 2, we don't change any of the solutions because we haven't changed the solutions to that equation, right? Multiplying both sides by something other than 0 doesn't change the solutions. Now, finally, but not quite so obvious that it doesn't change the solutions, we can multiply one equation by something and add it to another, while leaving the first equation unchanged. And we'll see an example here, if what I'm saying doesn't make sense. And when we see the example, I'll try to justify that it doesn't change what the solution set is. And in the end, what we're going to see, although we won't really demonstrate it until next week in a later video, is that we can always take a linear system and through a series of these elementary operations, transform it into an equivalent system that's in echelon form, maybe even in triangular form. And so this will allow us to solve any linear system that we have. So let's go back to our example. How am I going to transform this to echelon form? Well, the first thing I'm going to do is I'm going to move it over to the side because I want to have some space to write stuff. So step 1, if I want this thing to be in echelon form, there's a problem that the leading term in equation 1 is not x, right? So I want to move one of these other equations up top. So step 1 is going to be to switch equation 1 and equation 2, which we've already justified it. That does not change the solution set. So I've switched the first two equations and I haven't changed the third equation. All right, so that's my first step. My next step, I don't have to do this, but I'm doing it because I want to demonstrate it, and there's actually good reason to do it. It kind of makes sense. I notice that this equation at the top is all divisible by 2, and so I'm going to get rid of that. And if I'm getting rid of the fact that these are all divisible by 2, why not make this positive? So I'm going to multiply equation 1 by minus 1/2. Right, that'll get rid of that minus 2 and all the other 2's. And so this will only change equation 1. So this will turn into x minus 2y equals -3. And I still have y minus 5z equals 4, and minus 3x plus 6y plus 2z equals -2. And these systems are all equivalent. So this system right here has the same solution set as this system, because being equivalent satisfies the transitive property, right? These two systems are equivalent because all I did was switch two equations. These two systems are equivalent. All I did was multiply one of the equations by a non-zero constant, and that means that our first and third equations in this line are also equivalent. Now the final thing to get this into echelon form, and I set this one up so that it would not take too long, but if I want this to be in echelon form, I can't have this 3x as a leading term of the third equation, right? Because that's not what echelon form looks like. I already have x as my leading variable for equation 1, y is my leading variable for equation 2. I need to bump it down to this z. And the way I'm going to do that is by adding a multiple of equation 1 to equation 3. And when I do this, and this is where it's nice to see an example, what I'm saying is that I'm not changing anything other than equation 3. Equation 1 will still stay as it was. Equation 2 is not even part of the process. It remains untouched, but I'm adding 3 times equation 1 to equation 3. And so let's do that calculation over here. What I'm saying is I'm taking 3 times equation 1 and I'm adding this Adding equations is probably not mathematically totally correct, but I'm not really that worried about this. And what do I end up getting? Well, I get cancellation of the x terms and also the y terms. And this is what I get. 2z equals negative 11. These two systems are equivalent. They have the same solution set. Why is that true? Well, one way of thinking about it is that I can go back and forth between these. That is, in doing this, in adding equations to each other, I'm never really concerned about losing solutions. So that is to say, if I have a set of x, y, and z that makes this equation true, when I start adding multiples of equations together, it's still going to be true, right? If equation 1 is true, then equation 1 is true, and if equation 3 is true, then adding those together will still be true. The concern is that you can add solutions. That is that you can actually end up with more solutions by doing this sort of stuff. But I'm not worried about that because I could actually go backwards, right? So if I'm looking at this equation and you said, well, how do you know how to go from this back to this? Well, I went forward by adding equation 1 to equation 3, and so I can go back by subtracting equation 1 to equation 3. So if I wanted to recover this system from this one, the way I would do it is by subtracting 3 times this first equation from the third equation, and then I would end up with this. So this is why they have the same solution set. And this thing's in echelon form, right? In fact, it's in triangular form. And so we can now back substitute and solve. I'm not going to go through that process. I'll leave that to the viewer, right? If you want to go through, back substitute, solve this system, that's a great exercise. You'll get a unique solution because it's a system in triangular form, and you can check your answer, plugging your answers back in. This will always be possible. That is, here I worked with a relatively simple system, right? There's only 3 variables, 3 equations, and I only had to do a few steps. I wanted to do an example of each type of operation. And you may look at this and say, okay, well, yeah, I can kind of see how you took this and how it made sense to do each step, right? How to switch the equations, multiply to get rid of a common factor, and then how we added one to another to get rid of this term. And maybe you can even start to see that it actually is always going to be possible to get to a system in echelon form by doing a sequence of these. The real question then is, how do you actually do that? That is, if you don't have just 3 equations and 3 variables, but maybe you have 10 equations and 20 variables, how do you know what to do? You have so many options for what you could do here. And that's a topic of a later video. That is, what is the process for going step by step and always knowing that you're doing the right thing, not just hoping that something's going to work. We'll talk about that later. But just know for now, it is always possible. And for now, if you're given a system, try to think about what operations, switching to equations, multiplying an equation by a non-zero constant, and adding a multiple of one equation to another will get you closer to echelon form. Right? Each step here is in some sense getting us closer to echelon form until we're there. All right, it's already been a long video, but I wanted to do 2 final quick examples, and they're real fast, but they highlight important things that can happen. Because so far all we've seen are infinitely many solutions and exactly one solution. And you might wonder, what's going to happen if we have no solutions? So this system will have no solutions, and it's a really simple one. When we try to solve it, what happens when I try to get rid of this negative x1? So I'm going to add equation 1 to equation 3, And what I end up getting here, when we add equations to others, we don't change that equation, right? Equation 1 remains the same. Equation 2 is not even involved. And then what do I get for equation 3? Well, I get x plus negative x, 2y plus negative 2y, negative z plus z. These things all cancel. I get 0x plus 0y plus 0z equals, and then on the right-hand side, I get 4. Written another way, this says that 0 equals 4, which is not true. 0 is not 4. What does this mean? This means that we have no solutions. And this is what will always happen when you have no solutions. You'll try to transform your system into echelon form, and you'll end up with an equation that is not true. That is, you'll have 0 is equal to some number other than 0. So that was one thing I wanted to look at. And then the final thing is, well, couldn't you end up with 0 equal to 0? Yeah, sure. Let's see what happens when 0 equals 0. I mean, 0 does equal 0. But if I take this system and try to transform it into echelon form, it's really the same system as the other one, just changed slightly. I'll do it by adding equation 1 to equation 2. And what I'll get is that the first two equations, again, remain unchanged. But the third one, I don't know why I wrote that out. That's not what it turns into. When I add these together, everything cancels, right? X plus negative x, 2y plus negative 2y, negative z plus z, 1 plus negative 1. And so the bottom equation becomes 0 equals 0. 0 equals 0 is not a problem. This is true. And so how do we proceed from here? In the future, we'll be doing these sorts of things where it actually makes sense to leave the 0 equals 0. But for our current purposes, for working with systems of linear equations, this equation tells us nothing. In other words, all values of x, y, and z make this equation true. It's just already true. There's no variables. So what would we do next? We would say, look, we don't need to work with this. We're going to get rid of that row. This is only for 0 equals 0. Right? We would just say, okay, that equation's not helping us. We don't need to work with it anymore. So that's what happens if we get a 0 equals 0 row. Right now, we just ignore it. Later, in different similar situations, it'll make sense to keep it. But for now, we're going to just ignore it. All right, so I think I've accomplished what I wanted to in this video. We looked at systems that were easy to solve in triangular form, which is a specific example of echelon form. Saw how to solve those with back substitution, and saw that it's possible to take linear systems and, through a series of elementary operations, transform them into other systems that are easier to solve. And in particular, you can always get to a system in echelon form. What I haven't done is talked about how we actually guarantee that our sequence of operations will take us to a system in echelon form. And again, for now, what I recommend is just do your best. We'll be working with smaller looking systems where you can hopefully see the path ahead of you and say, okay, yeah, if I do this sequence here, this will get me to echelon form. In a later video, I'll look at an algorithm so that we never have to wonder, so that we always know that what we're doing will lead us to a system in echelon form.